So hopefully everyone's weekend was good. Okay, so today we're going to take up the participation questions from last time. So hopefully everyone submitted those. And then I was going to take up assignment 1B in class, but I don't really feel like doing that. So I'm just going to post the solution set for you guys, and then we'll save a bit of time. So I'll do that later on today. So that's just a PDF of the solution set. It'll be posted just where the assignment is posted. And then we're going to cover integration by parts. So a pretty light day. Okay, so let's start with, let's share screen and let's go to the participation questions. And I'm a bit tired today, apologies. So if I stutter or am inarticulate, sorry about that. Okay, so first let's do a recap of the two formulas from last time. So it was inverse trigonometric functions. So they were a inverse sine function, the integration formula for that, and then it was also the inverse tan function. So here it was. So if you have something of the form du over square root of a squared minus u squared, if you have something specifically in that form, then you get sine, and then you integrate it, you get sine inverse of u over a plus c. But it has to be very, very specifically in this form, because sometimes it looks like like you can use this, but sometimes you can't. Like sometimes it looks like it, but you'll have to use like a logarithm formula can look really similar to this. So you have to kind of discern the difference between various forms. And then the next one is du over a squared plus u squared equals 1 over a tan inverse of u over a plus c. So that it's different from the other one. Of course, you have no square root on the bottom, and then you also have a plus sign on the bottom. So the difference between them is, at least there's the pretty distinct differences. So it was page 870, 5, and 7. So let's try to squeeze 5 down here, just so we don't have to, actually here, I'll erase one of the formulas. So this number 5 uses the second formula. So let's just erase the first one, just for some room. Here we go. So this one was integral of dx over 64 plus x squared. Okay, so that's a pretty basic one. Okay, so in this case, you could, if you want, you could rewrite it a little bit. You could take the 64 and just write it as 8 squared, because that's the same thing. So let's just do it like that, just so you could see that it is indeed in the correct form. So this is 8 squared plus x squared, and that's the same thing. But now if you compare it to the form below, you can see that a is just 8 and u is just x. And you have to remember that in the form, you have a squared at the bottom. So in this case, 64 is a squared. 8 is a. So 8 is what you use in the actual answer. So again, you got to be careful. You got to look at these closely. Okay, so this will be, I guess there's nothing else we have to do. Everything else is good. So let's just plug everything in. So 1 over a will be 1 over 8 tan inverse of x over 8 plus c. And yeah, there's no way to simplify that, so it would just stay as it is. So that one was not too bad. The next one is interesting. It's a little more complicated, but it's not too bad as well. So let's do the next one. So number 7. So again, just for room, I'm going to just get rid of this, and I'll write down the, in this case, the sine formula. Sine formula is integral of du square root of a squared minus u squared equals sine inverse u over a plus c. Okay, so the question number 7 is integral of 8x dx over square root of 1 minus 16x to the 4. Ooh, that's a twist. 1 minus 16x to the 4. So this is slightly concerning because you might look at it and say, well, it's not really in the form of like u squared, but it technically is. You just have to rewrite it a bit. So let's do that. And both of them appear to not be in the correct form, but they can easily be rewritten as squares. So let's do, and then for the top, I'm just going to keep the top the same for now because I don't know what type of adjustment we'll have to do later. Okay, so square root of, so for the 1 is just 1 squared because 1 times 1 is 1. So that one's a trivial one, I guess you could say. So 1 squared, so that's an easy rewrite, minus, and now let's just do this off to the side. So 16x to the 4. So how do we write that as something squared? So in general, if you have something like this, what you can do is you could surround both the number and the x with brackets. So let's do that. So what you can do is you could just surround them with brackets, put a 2 right here, and then you'll have to adjust the numbers. So for example, let's see, for the 16, 4 squared is 16. So you just put a 4 right there, and it ends up being the same thing. And then for x squared, you could put, or sorry, for x to the 4, you could put an x squared right there. So if you kind of imagine this being distributed to both of these, you end up getting the same thing as what you have above. But now at least it's in the form of something squared. So yeah, that's the same thing. 4 squared is 16, x squared squared is x to the 4. So that, okay, so that works. So we could do 4x squared squared. So now it does appear to be in the form of something squared. And this formula, let's see, let's write a generic version of this formula just so everyone kind of knows it. Yeah, basically it's just if you have something like x, let's say to the n, y to the n, it's equal to x times y to the n. So you could kind of take, in regard to multiplication, you can kind of take the exponent out of an expression as long as you surround it with brackets, and it ends up being a useful way to manipulate various expressions. Yeah, that works with multiplication. It doesn't work with plus or minus though, in general. Okay, so now we have it in the correct form, but now we need to actually, we still have to check that it's in the correct form because you need a du at the top, and that's always something you have to check for. So let's just establish what u is exactly. So if we compare the form to the specific integral, u is 4x squared. U is just whatever is being squared. So let's just write that down. U is 4x, squared, sorry, so du is going to be, oh, actually, hold on, will this work? Oh, yes, yes, absolutely it does. Sorry, I was seeing a mistake, but yeah, it's not, don't worry. Okay, sorry, I messed myself up. Okay, let's do du. So that should be, so the 2 comes down and then subtract 1 from the exponent. So that's going to be 4 times 2 times x dx. So this is just 8x dx. Okay, yeah, I was concerned because I was like, what the heck? There's an x right here. That's going to screw up our entire question. But indeed, there is an x at the top. So that's, yeah, so everything is good. It's actually perfectly in the correct form now. They even were nice enough to put the 8 on top for us. So we don't have to do anything. So we could just directly go to the answer now. So the answer will be, let's just write the generic form, sine inverse of u over a plus c. So u in this case is going to be here. Let's just write, so u is 4x squared, a is just 1, just so we know. Okay, so this will be sine inverse. So u is 4x squared over a, which is 1. Okay, so there's no point in writing anything over 1. So yeah, I'm not going to write that part here. Let me just erase this line right here. Oops. 4x squared. If you want, you could write it over 1, but it doesn't make any difference. Plus c. So that's what we get for that. So sine inverse 4x squared plus c. So these could be interesting questions because a lot of them, when you look at them, it's like, well, they don't appear to be in the correct form, but you just have to have some algebraic knowledge, and then you can manipulate things pretty easily. Okay, Let's see. So I guess that's it for the participation questions. So let's go to, should I go to the actual PowerPoint or should I? It's a tough one. Let's just stay with a whiteboard. Okay, so this is 28.7, I think. Yes, 28.7. It's integration by parts, which is a formula for breaking down an integral into multiple parts in order to make it easier to integrate. And it's not super complicated. It has some difficulties. So first we're going to start off, as we usually do, by looking at a derivative formula. And then we'll kind of reverse the derivative formula and establish an integration formula. Usually I like to do that just to give some context as to where the integration formula is coming from. So let's look at the formula for the derivative of the product of two functions. So let's look at the derivative of, let's say, u times v. Okay, so what is the derivative of u times v, where u and v are just whatever generic functions? So the formula is u times the derivative of v plus v times the derivative of u. So it's a pretty easy formula to remember because it just alternates pretty much. And yeah, so that is it's called the product formula for derivatives. So u times v, derivative of that is u times derivative of v plus v times derivative of u. Okay, so far so good. So basically what you can do is pretty easily rearrange this into an integration formula. You could, I'm not going to go through the details. I'm not going to bother directly deriving it, but you could basically just, apply an integral here, 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 rearrange it a little bit, and we get the following integration formula, which is our integration by parts formula. And it's very, very, very specific. So integral of u dv is equal to u times v minus integral of v du. So that is our integration by parts formula. So the first thing I want to point out, again, it's super, super, super specific. It has to be in this form right here. So u is just u, it's whatever generic function, but the other one is specifically in the form dv. So the other one, you have to view it as being already a derivative, which is kind of a weird way of viewing it, but that's the best way to view it. So it specifically has to be in that form. And then you just have a u right here. You have v right here. So in this case, you're going to have a dv, and in the answer, you're going to have a v. So when you're doing this, you actually have to take an antiderivative as you're solving it. And then you have minus, and then you have integral of, and then within that, you just have v, and then you have the derivative of u. So within these questions, you have to kind of, well, of course, we'll do a bunch of examples, but you have to pick a u, and then later on, you'll have a du in your answer. You also have to pick this part right here. You have to assign something as dv, and then in your answer, you'll have just a v. So in that case, you have to take the antiderivative of that. So it's, again, super, super specific in the way that it's set up. Yeah. So I think what we should do is let's just do kind of an easy first example. And I'm just going to erase this, and then I'll write the formula at the top. And I already forget it. Here it is. Okay. Yeah, this formula is so hard to remember, to be honest. Like yeah, I can never remember it. So u dv equals uv minus integral of v du. Okay. And so for this, basically what you'll do with each example is you'll pick a u, and then you will, at the start of the question, have to find du, because that's, as you can see, that's in the answer. You'll also have to assign a dv. This is how I visually view it. You'll have to assign part of it as being dv, and then you'll have to take the antiderivative and specifically find v. So it's like in one case you're going forward, and in one case you're going backwards, and then you just plug everything appropriately into the right side of the formula. So that's how I view it. But let's do a specific example. Okay, so this one is, it says integrate x sine x dx. X sine x dx. Okay, so the first thing you have to do is pick u and pick dv. A lot of people think that you're picking u and v, but again, if you look at the left side of the integration formula, it specifically has integral of u dv. So in this case, let's start by picking u. And when you pick u, you pick something that's easy to take the derivative of, because you're going to have to take the derivative of it. And for picking dv, you just pick whatever would be easy to take the antiderivative of, because usually there's multiple ways of doing this, but that's always the logic that you follow. Whatever is easy to take the derivative of, use that for u. Whatever is easy to take the antiderivative of that, use that for dv. So for this, I guess the obvious choice would be, let's just do x as u, because it's pretty easy to take the derivative of x. So let's pick that for u. So let's say u is x. And then you have to find the derivative of that. So du is just going to be dx. So that is not too bad. So that's the first step. And then for the rest of it, you assign, so the rest of it is this, you specifically assign as dv. That's the part that everyone has trouble with. They have trouble with, for some reason, everyone wants to assign that part as being v, but you don't do that. You assign it as a derivative. So let's do that right now. So in this case, dv is sine x dx. So you have to set it up that way. And then what you do is you go backwards to find v. So it's a weird way of doing it, and it throws a lot of people off, but that's just, you got to do it that way. So what is the antiderivative of sine x dx? So derivative of sine is cos, derivative of cos is minus sine. So the antiderivative should be minus cos. Yes. Minus cos x. So let's just double check that. Derivative of cos is minus sine. Okay, that works because the two minus signs would cancel out. So that works very well. Okay, so that is how you initially set it up. Again, I like this visual way of kind of one goes forward and the other goes backwards. The textbook doesn't use this visual way of doing it, but they probably should, because I like it. It's a good way of kind of visualizing everything. And then now what you do is plug everything in. So let's just write the generic right side of the equation. uv minus integral of v du. And now let's just very, very slowly plug everything in, because another mistake everyone makes is they plug everything in totally wrong. Because there's so many different ways, like there's so many mistakes you can make in this case, because it's a pretty complicated formula. And there's 4 different things that you have to plug into it. I guess technically there's 3 different things. There's u and v and du. So yeah, lots of ways of making mistakes in this case. So u is x. So x. V is minus cos x. So let's write that, minus cos x. Good. Minus integral of, and then v is, again, minus cos x. And then du is dx. So that's actually nice. So basically what you're doing is you're taking an integral and breaking it down into multiple parts. And then in this case, this integral that you end up with in your answer will be easier to integrate than the original question. So that's you're kind of reframing an integral. So it kind of seems like you're making it more complicated, but yeah, it'll resolve pretty easily, at least in this case. So let's just, let me write this. I'll just keep it here. So let's do, for the first part right here, you don't have to do much. It's not an integral. You just, write it so that it looks nice. I'm just going to write, what's the best way to write this? I'll just write it as minus x cos x. So not much that you can do with that. And then for the next part, there's a minus sign here and a minus sign here. I wonder if I should just cancel those out. Let's just cancel those out. So let's write plus integral of cos x dx. And now the last thing you do is you integrate the cos x dx. So integral of cos x should be just sine, right? Because derivative of sine is cos. Yep, so it should just be sine. So this will be minus x cos x plus sine x plus your constant. And let's just double check that that's right. Yes, looks good. So that's the basic layout of how you do these. So again, I think the primary mistake is that most people for this question, they'll correctly pick u, but then they'll choose that v is equal to sine x dx, and that's their first mistake. You don't assign it as v, you assign it as dv, and then you find v. So again, it's a weird little thing you have to do, but that's the main mistake that everyone makes. So let's look at another one. And the next part in the slide, I'll just read it. It has two general guidelines for how to pick u and how to pick dv. So choose u so that you can take the derivative of it pretty easily. And then choose dv so that you can take the antiderivative of it easily. And that's the basic guideline for picking u and picking dv for these. Sometimes there won't be a logical way of picking them. And in that case, you just do it however you want. But typically there will be like a pretty clear way of doing it. So let's do, what else do we have? Actually, yeah, that's here. Hold on, I'm going to do an illustration of that. So in this case, we picked u as being x, and that was logical because du is just dx in that case. And then for dv, we picked the rest of it. We took the antiderivative, and everything was good. You could have hypothetically picked it a little bit differently, but it just would have made the question more complicated. What you could have picked is you could have assigned them differently. You could have assigned u as being sine x, and then you could have taken the derivative of that. And then you could have picked dv as being x, and then you could have taken the antiderivative of that. So in this case, there would have been two ways of doing it, but I chose the other way because in this case for u, it would have been equally simple, because taking the derivative or the antiderivative of something like sine or cos, that's equally simple. But in this case, taking the antiderivative of x kind of sucks, because then you're going to get 1/2x squared. And it's way simpler just to do it this way. It's way simpler just to have a dx that you have to deal with rather than having a 1/2x squared. So again, you want to pick the simplest way of doing it. Yeah. So let's do another one. So this one, this one's interesting because there's only one way of doing this one. Okay, again, let's just write down the formula, pretty much just because I can't remember it. Here it is. U dv equals uv minus integral of v du. And the question is integral of square root of x times ln x dx. So in this case, there is a pretty clear choice. So you're going to have to pick one that it's easy to take the derivative of, and one that it's easy to take the antiderivative of. But in this case, ln x kind of restricts you a little bit, because like you could take the derivative of ln x, that's just going to be just 1/x, but you can't really take the antiderivative of ln x. So the choices here are going to be clear, because even I don't know the antiderivative of ln x. I'm not sure what it would be. Yeah, so in this case, it's very clear, choose u as ln x, because if you choose it as dv, you're kind of screwed because you don't know how to take the antiderivative of it. So u is ln x, and now let's find du. Let's go in this direction. So du is going to be, so derivative of ln x is dx over x. So good. And then the next part, which is the square root of x, will specifically be assigned as dv. Again, you don't assign it as v, you assign it as dv, and then you deduce what v is. So I'm just repeating that because it's the most common mistake. So this is going to be, okay, so we're assigning dv as square root of x, and then we kind of do our little backwards maneuver, and let's try to figure out what's the antiderivative of square root of x. Well, we know the antiderivative formula for that is you add 1 to the exponent and divide by that number. Let's kind of do that off to the side. So square root of x, let's write it with an exponent. A square root is just an exponent of 1/2. So let's write it like that. So add 1 to that and divide by that number. So it will be x to the 3/2 divided by 3/2. But dividing by 3/2 is the same thing as multiplying by 2/3. So let's just do that. So 2/3. Okay, so that looks, yep, so that's what we do for that part. So v is going to be 2/3 x to the 3 over 2. So that's not too bad. And then we plug everything into our formula. So let's do that. Let me just erase part of this. Okay, let's, so this is, here we'll just continue on with the actual, here's the formula right here. So let's just plug everything in. Okay, so, and again, plug it in carefully because usually it's very rare that people get the correct final answer for these, because they'll either make a mistake when they're setting up U and dv, or they'll make a mistake plugging stuff in. So U is ln x, V is 2 over 3 x to the 3 over 2 minus integral, and then within the integral V, so that's again 2 over 3 x to the 3 over 2. Good. What else? And then du, which is dx over x. So dx over x. Okay, that's not too bad. That's, yeah, that'll be fairly easy to integrate. Now for the first term, again, the first term it's good to go. You don't have to really do much with it. Just make it look nice. What I would do is I would switch around the term a little bit, because I don't want the reader to think that the 2 over 3 x to the 3 over 2 is in the ln. The only thing inside the ln is just the x. So I would rearrange it a little bit just to make it clear to the reader what's in ln and what isn't in the ln function. So yeah, let's rearrange that a little bit. Let's just write that as 2 over 3 x to the 3 over 2 ln x. I think that looks a little bit better. Next part, we can simplify the integral a little bit before we integrate it. And I'm just trying to figure out, should we take the 2 over 3 out of it, or should we keep that in? Let's just take it out of it for now. So minus 2 over 3, we'll leave it out and it can just sit in front of the integral. Okay, so now the rest of it, and this is, sorry, this is a 3 right here. Okay, so the rest of it is, you have x to the 3 over 2, and then you have an x on the bottom. So you can cancel those out partially. So you can get rid of this x right here, and you can decrease this exponent by 1. And that's just some basic cancellation. So this will be just 1 over 2. So let's put that in. So x to the 1 over 2 dx. Okay, so we haven't actually integrated it yet. So of course we have to do that. But that's a fairly easy integral. It's just the general power formula. So you just add 1 to the exponent and divide by that number. So in this case, it's actually kind of ironic that you end up taking the antiderivative of x square root of x twice. But that's more or less just a kind of a coincidence in this case. So let's write out this, keep running out of room. So 2 over 3 x to the 3 over 2 ln x minus 3, or 2 over 3. And now let's integrate this. So add 1 to the exponent and divide by that number. So that'll be x to the 3 over 2 divided by 3 over 2, but that's the same thing as multiplying by 2 over 3. So another 2 over 3 kind of pops out. So let's just write that right here, 2 over 3, right there. Good. And now the only part we have to simplify is just the last expression, because it looks weird having 2 over 3 times 2 over 3. So here, I'll just write the final answer and I'll simplify the last expression. So 2 over 3, x to the 3 over 2, ln x minus, okay, so for multiplying two fractions, you just multiply the top numbers and then you just multiply the bottom numbers. So 2 times 2 is 4. 3 times 3 is 9, and x will just be x to the 3 over 2. And that's your answer. In this case, you can simplify it a little bit. You could factor some stuff out if you wanted to. You have an x to the 3 over 2 in both of these, so you could factor that out if you wanted to. You also technically have a 2 over 3 in both of these, because one has a 2 over 3, the other has a 4 over 9, which kind of has factors of 2 and 3 on the top and the bottom. So you could factor out a 2 over 3 out of both of those, but I think we'll just leave it like this. I don't think factoring it really simplifies it all that much. So this is fine as an answer. So hopefully everyone is starting to see how these questions function. Oh, yes, very good. I forgot about the plus C. My student reminded me. They just asked, does the plus C affect being able to factor it? If you factored it, you would just factor this part, and the plus C would just remain as a plus C at the end. Yeah, with the plus C, you have a lot of freedom because it's an arbitrary constant. So even if you hypothetically imagined factoring something out of it, if you factor something out of an arbitrary constant, the answer is an arbitrary constant. So it never really matters that much, even if you wanted to do something with it. Okay, the next one is interesting. The next one is another one where you really only have one choice for the choices of U and V. At least that's what it looks like. So let's do that one. Okay, so it says integrate. Let's do the formula first. And so I don't run out of room. I'll try to write everything better. Let me just erase this. Let's just write everything on the left to start with. Integral of U dv equals U times V minus integral of V du. So far, so good. And then we're going to do, so the question is integral of sine inverse x dx. Okay, so the first thing you have to do is you have to pick U and pick dv. So in this case, the sine inverse x is going to kind of restrict what you can do, because we know how to take the derivative of that. That's listed in our derivative formula sheet. But for the antiderivative, I don't know that off the top of my head. Plus, that's literally what we're trying to find, because the only other part of it is just the dx part. So in this case, you got to pick U as the sine inverse part so that you can take the derivative of it. So U equals sine inverse x. And the derivative of du is, or sorry, the derivative of du is dx divided by 1 minus square root x. And we've seen that before because that's where we got our inverse integral functions from. That's where they come from, just the derivative formula. Okay, and now at this point, a lot of people might be like, hey, what the heck? There's nothing left. What do we pick for dv? Well, that part's really easy. For dv, you just pick dx because that's the only thing left in the expression. So you can do stuff like that. So dv is just dx, and then work backwards and figure out v. And that's easy. V is just x, because you could just kind of imagine the d's canceling each other out. Or you could just take the antiderivative of each side. So that's the only choice you have for that regardless. And now we plug everything in. So let's do that. U is sine inverse x. V is x. And I'm just going to write the x on the left side, just again, so the reader doesn't think that there are two x's plugged into sine, because that wouldn't make any sense. And then minus integral of, so in the integral we have v, so that's x, let's write that, x. And then in the integral we have du, which is dx over square root of 1 minus x squared. Okay, so that's what we have for that. And hopefully that is something that will be easy to integrate. It looks, on the surface, it looks like you would use a inverse trig function for that integral, but you don't. I think for that, you're just going to use, I think you'll just use the ln function. Yeah, it'll just be the, yeah, so let's do that. And then for the left part right here, this just stays as it is. It's perfectly fine like that. Okay, so yes, I think we use our logarithm function, or our logarithm integration formula. Let me just look that up just to make sure I remember it correctly. So let's, the formula for that is du over u equals ln of absolute value of u, and then plus c, but for the sake of room, I'm just going to leave that out. So I think that's the correct formula to use. Let's double check that. Is that the correct formula? That's a tough one. So is that in the correct form? Actually, no, I don't think it is. So in this case, I think we'll have to use, which formula do we use? Let's see, I think maybe the general power formula will be the one that we end up using. I think so. Let's try that one. General power formula, let's write that down. Eraser, I'm just gonna erase this part. Indeed, someone also pointed out that it appears to be in the form of an inverse, in this case, it would be inverse sine function, but I don't think that's what you would use because it doesn't quite work. The reason it doesn't work, it would work if this x wasn't here. That's the problem, because let's actually go through it and I'll show why we can't use that particular formula because that x messes everything up. So if you did want to use the inverse trig formula, let's just write it down. Where is it on my formula sheet? Here it is. So yeah, if you did want to use that, it would be integral of du over square root of a squared minus u squared. So in this case, if you wanted to try that formula, you would just have u being x. And sorry, my notation is bad. In this case, I'm double using u because we already previously used it. Sorry about that. That's bad notation, but just for simplicity, I'll keep it like that. And then du would be dx. So that's where you get screwed up because that's not what you have on top. You don't just have a dx on top, you have an x dx. So that completely messes it up. So it looks like it's in the correct form, but it's just not quite there. And there's no way to get rid of that x on top because it's not like a constant. You can't really take it out of the integral. So that's why I'm not using the inverse sine formula. But it's a good suggestion because it looks like it would be the solution. Okay, so let's just get rid of that. And let's do the general power formula. And let's see if that works. Where's the general power formula? Again, I'll just write it down just for the sake of, okay. So general power formula in general is u to the n du equals u to the n plus 1 divided by n plus 1 plus c. So you add 1 to the exponent, divide by that number. So let's see if this is in the correct form. Does it initially look like it is? Because you have a square root on the bottom, but you can actually bring that up to the top. You can write a square root as an exponent of 1 over 2, and you could bring the whole thing up to the top as long as you change the sign on the exponent. So this is technically, you could write it as, let's write this, I don't want to have to rewrite the whole thing, darn it, okay. So yeah, let's just rewrite it down here. So x dx over square root of 1 minus x squared can be written as integral of x times bracket 1 minus x squared to the minus 1 over 2 dx. So that's the same thing. Again, a square root is just an exponent of 1 over 2. And I also brought it up to the top and I changed the sign and I made it negative. And that's technically the same thing. So now it looks a bit more similar to the general power formula, because at least we have like a u to an n in this case. And then we just have to check if we have the appropriate du. So in this case, u would be, and again, I'm sorry for double using u. As a mathematician, I feel bad for double using a variable. So u is 1 minus x squared. So du would be minus 2x dx. Good, that's actually very, very good. We have an x dx in there, and that's exactly what we need to have on top. So that is the solution for that little part, is the general power formula. But that's actually a really good example because like initially it looks like an inverse sine function would work, then it looks like a logarithm function would work, and then it just ends up being actually just the first formula that we originally looked at. You do have to do a bit of an adjustment here because du is minus 2x dx, and there's no minus 2 in your integral. So you just have to do one of the basic So in this case, I think I'm just going to go up to the top. So we need a -2 in there. So what's the easiest way to do this one? Because there's already a minus sign right here. So maybe we should just move the minus sign into the integral and then just put a 2 and then just put a 1/2 out front. Maybe that's the best way to do it because the minus sign is already there. We might as well use it. Let's do that. So this is, and I'll just write the whole thing. So x sine inverse x minus, plus integral of, and now let's write this as, so minus, and we also need a 2, so I'll put -2x dx, and then I'll put a 1/2 right here. And this is over the square root of 1 minus x squared. Okay. So that's good. So it's the same as what it was because I just moved the minus sign. The 1/2 and the 2 offset each other. So that's perfectly good. So now let's apply the general power formula. And I keep running out of room. It's driving me crazy. Okay, where should I do this? Let's just do this on the left side. Let's just erase this part. Okay. So let's write out the whole thing. Oh, I didn't erase the whole thing, sorry. Erase this part. We need that part. Let's erase this. Okay, so whole thing is x sine inverse x plus 1/2. And now let's apply the general power formula. Let's apply it to, let's just look at this part. It'll be easier to do it that way because I wrote this part with a classic square root. So let's look at this one. So add 1 to the exponent, divide by that number. So it'll be add 1 to -1/2, that'll be 1/2. And then dividing by 1/2 is the same thing as multiplying by 2. Okay. So that will be 2. And then u is 1 minus x squared. And then it'll be 1/2. Hopefully I got that right. Yeah, add 1 to the exponent, divide by that number. Okay, very good. And then you just have to simplify this one. And let me just double check to make sure I didn't make any mistakes. Let's see. So far, so good. And yes, perfect. Okay, so some obvious simplification that you can do here. There's a 1/2 and there's a 2. That you can cancel those out. So goodbye to those. And I guess there's not really much else. For this part right here, if you want, you could keep it in its exponent form. You could just keep it as a 1/2. If you want, you could write it as a classic square root. It makes absolutely no difference. It's the same thing. And I should write plus c at this point. I should technically have it. You should technically have the plus c right when you integrate it. So for this, I think for the final answer, let's rewrite it a tiny bit. Let's just do x sine inverse x. And let's just write this part just with a square root, because that was what they originally used in the question. So let's just use that. But it doesn't make any difference. And yeah, so that is, yep, that's everything for that one. So that one, there was part of that was a bit of a tough one. Sometimes the general power formula can be like deceiving because like a lot of the times you forget about it. A lot of the times it doesn't even look like it would apply. And then it's like you're trying to figure out what formula. And then at the end, it's like, oh, it was just the first most basic formula that we looked at. Let's see. And I think we'll do a few more and I think we'll just call it a day. Okay, let's look at the textbook. Let's see if there's any interesting ones here. Did that one, did that one, did that one. Don't feel like doing that one. Integration by parts twice. Ugh. Let's see, I'm just trying to find another basic one. I'm not gonna really go too advanced with these just because it's already a topic that people make a lot of mistakes with. This next one is, maybe we should do, so integration leading to an equation. That's a really interesting one. Should we do the integration by parts twice? Let's do example 7, because it's an example that if you did it initially, you'd get to a point where you're like, man, I'm totally stuck on this question. I'm going in circles. And then there's like one tiny thing that you have to do and it instantly solves it. So it's a really interesting question. Clear this. Let's write down our formula. Where is it? Here it is. So integral of u dv equals u v minus integral of v du. Okay, so example 7, it says integrate e to the x sine x dx, which initially looks like a pretty convenient, easy one. There's nothing super complicated in the actual integral. So e to the x sine x dx. Okay, so for this, it looks like the choices between what you pick as u and dv in this case, it looks like they're pretty much equal among each other. In other words, you could go either way and it'll be the same answer. Because like e to the x, it doesn't matter because its antiderivative, it's the same as its derivative. So that's not any more complicated in one case or the other. And for sine x, taking the derivative is also just as easy as taking the antiderivative. So in this case, you could pick u as ex, or you could pick ex as dv. It doesn't make any difference. So I'll just do what they do in the textbook. In the textbook, they pick u as sine x. And they probably just do that maybe just to avoid an extra minus sign. That might be the only logic they're using. Anyways, again, doesn't matter. So u is sine x. So du, so derivative of sine is cos. Yeah, I think that's why they chose it this way, because if you chose it the other way, you would take the antiderivative of sine, which is minus cos. So I think that, I guess one way, I guess picking u as sine x in this case, you could argue is slightly simpler because it avoids a minus sign. And then dv will be e to the x, e to the x dx. And then the antiderivative of that one's pretty easy. In that case, it's just itself, e to the x. And then the dx, because you're taking the antiderivative, kind of just like regresses and disappears. Okay, so that's a fairly easy setup now. Sorry? Yes. Actually, hold on. Should there be, I guess, I guess technically, yeah, there should be a dx right here, but doesn't, yeah, it doesn't matter too much. Okay, so let's plug everything in. Let's just do this at the top because we already have the formula. So u is sine x, v is e to the x, minus integral of v is e to the x, and du is cos x dx. Actually, yeah, you're absolutely right about that. Yeah, you need the dx because you need that in your integral. Good point. Okay, so now let's do this one. So again, it doesn't look too bad. You got the sine x e to the x part, which you could just leave it as it is. Again, I would switch the e to the x to the left side just so it's clear that it's not inside the sine function. And then we'll have to integrate e to the x cos x dx. And for that one, it looks like we'll have to use an integration by parts formula again, because it's so similar to the previous one. I don't think there's any direct way of integrating that. Otherwise, we would have just done that originally, because it's almost the same as the original integral. So we'll have to do integration by parts twice. So let's do that. Let's just erase, I'm going to erase the original setup and we'll pick our new u and our new dv for this new integral. So I'll just erase these right here. So yeah, sometimes you'll have to do integration by parts twice, but I'm just doing this question because it's a very interesting curiosity. Okay, so for the left side, actually, I'm not going to rewrite this. For now, let's just pick a new u and a new dv. So let's see what they do in the textbook. So they stay consistent and they go, for u, they stick with the trig part of it. So for u, let's just pick cos x. And then du will be, so again, just to clarify, we're doing integration by parts twice. Now we're specifically doing it for this integral. And then du will be, so derivative of cos is minus sine x dx, good. And then dv will be the rest of it, which will be e to the x dx. And then you have to take the antiderivative of that. So v is equal to, in this case, just e to the x. Okay, and at this point, it kind of looks like you're going to start going in circles because it looks like you might just end up with what you originally had. Because once you do integration by parts here, there's going to be a sine x and there's going to be an e to the x. So it looks like you're going to just regress back to the original integral that you were trying to solve. And that's where the question is interesting, and that's where most students would be like, okay, it's going in circles, I can't solve it. And then it actually ends up being very easy. So let's do this part. And we got to be careful too, because what's the best format for this? So let's just do this integral separately because I don't want to have to keep rewriting the first term right here. So let's just solve this, separately. Okay, so integral of e to the x cos x dx. So we're just doing that part separately is, so the generic formula is u times v minus integral of v du. So let's plug everything in. So u is cos x, v is e to the x, minus integral of v is e to the x, and then du is minus sine x dx. So in this case, so you already have a minus sign outside of the integral, and you're going to have a minus sign inside the integral. So maybe we should just cancel them out right off the bat and just change this to a positive sign and just put in sine dx. Let's do that just to keep it simple right off the bat. So in this case, I'm canceling out the two minus signs. So we'll do sine x dx, just so I don't have to keep rewriting it. Okay, good. So you might notice that surprisingly, we have literally just regressed back to the original question, because look at this right here and compare it to this. And it appears that we've made absolutely no progress. That's what it looks like, but have no fear because we'll soon resolve this. So let's put this all together. And yes, we have to do it carefully. Let's do, okay, let's put this all together. So the original integral was e to the x sine x dx equals, and now I'm just going to write this right here, and then I'll plug in what we just solved for. So, and then for the sine x e to the x part, since I'm writing it down, I'm going to switch the e to the x. I'll put it on the left side. I just like it better on the left side, but it doesn't really matter. Okay, minus, and now here you have to be careful because it's minus this entire integral right here. So you have to put brackets right here, and then you could put in this entire part. So you have to be careful with stuff like that. So minus bracket, and now that part right there is cos. Actually, again, since I'm writing this, I'm going to switch the e to the x and the cos x. So yeah, e to the x cos x plus integral of e to the x sine x dx and bracket. So hopefully that's good. If I make any mistakes, let me know, because like in this case, all you have to do is like misplace a negative sign and you'll get stuck on it. So hopefully I haven't made any mistakes. And again, it still looks like you've made absolutely no progress. But again, we'll soon fix that. So let's erase part of this. I guess we don't need any of our original setup because we're already past that. So let's erase this. I guess we don't really need this part either because, yeah, so let's get rid of this. And now let's just continue simplifying the right side, and then we'll see what we get. So I'm just going to distribute the minus sign to both terms. And let's write out let's just write out the whole thing, because at the end you solve this in a very specific way. Okay, so integral of, and actually I guess we could just, all we need is just what we have at the bottom, right? So let's just erase everything except for that. Yeah, we got everything else. We have everything we need. So let's just erase this. And I'll keep the formula. Okay, so let's write out the whole thing and simplify it further. Integral of e to the x sine x dx equals e to the x sine x minus, so I'll distribute the minus sign, so minus e to the x cos x. And then what else do we have? And then that'll be also minus integral of e to the x sine x dx. So this is the part where you would probably arrive at this and you'd be like, okay, I give up. I did integration by parts twice and I just ended up with, now I just doubled the amount of integrals I have and I didn't even make much progress. But you could do a really clever trick at this point. What you could do is you could just take this integral right here and just move it over to the other side and just have it join its corresponding integral. So just move it over to the other side and change it from minus to plus, because when you move stuff around in an equation, you have to change the operation when you move it to the other side. So minus always changes to plus, multiplication changes to division. That's kind of just a general algebraic rule. But yeah, so this is the point where it looks like you're, all is lost and you're stuck, but you could do this kind of fun trick where you kind of just treat the integral as a, as just a part of an equation, and you just kind of move it around, and then we've actually almost solved it. We'll see what happens. So move it over, change it to plus. So you'll actually get on that side, you'll get the same integral plus itself. So you'll get two of them. So I'm just going to write a 2. Actually, maybe I should just not even bother rewriting this. Yeah, that'll be easy actually. So again, bring it over to the left side, and then you got 2 of integral e to the x sine x dx. So probably the best way, I'm going to be really lazy, and I'm just going to erase this part right here. I'm going to imagine that it moves over. I'm going to erase this arrow. I'm going to imagine that I add it to the left side, and I'm just going to put a 2 right here, because that's where you end up on that side, because you have that integral plus itself, so you get 2 of that integral. And now at this point, literally all you have to do is just take the 2 and move it over and change it to division, and you've solved your question. You've solved for the original integral. So it's a super cool question. So yeah, take the 2, move it over, change it. Since it's 2 times the integral, when you move it over, you change it to, in this case, division. So you always have to remember that rule. So integral of e to the x sine x dx equals, so I'm just going to put the 1/2 in front of both of them. You could put brackets around them and put the 1/2 out front. I'm just going to put it in front of both of them. And there, you've solved it. So that's, like I said, it's a really interesting one because you use integration by parts twice. You kind of go in circles. So you end up having the same term twice, and then you just add like terms. Despite the fact that it's an integral, you can do that, and then you've solved it. So very interesting one. Okay, so I think we could choose a due date for the last assignment. Let me just check what it is. Where is my assignment folder? Yeah, the last one is 1C. And it's a weird, yeah, it's exponential forms and integration by parts. I don't know why I decided to do it in that weird order, because exponential forms is like, we did that a while ago. But yeah, so for that, the due date will be next Tuesday, and we'll take it up next Tuesday as well. So it has to be in by then. Yeah, and I will, so that's already posted. So good. So I'll clarify that on Brightspace. Okay. And since I think we'll skip the participation question, since there's already an assignment for this one.
Did you say the assignment was posted already in your Dropbox?
I think so. Yeah, it's posted. Yeah, and then Dropbox is activated, as far as I remember. Yeah. But
I see the content, but not the Dropbox.
Let's see. Okay, it's possible that I forgot. Oh, I have it right here. Activities, Dropbox. Yes, you're right. I forgot to activate the Dropbox, so I will do that. I'll do that right after we're finished. Okay, stop sharing. Okay, so does anyone have any questions? Okay, so everyone seems good. Okay, and then Thursday we do the last part of this chapter, and then on Thursday we'll decide on when the first test will be. Okay, so everyone, I guess is there anything else? Okay, I guess that's everything. So everyone, thanks for coming and have a great day.
Thank you.